if you look up on the web, DASCH, Digital Access to a Sky Century at Harvard, that project is what this talk is about. Now, I took most of the photographs in here, and what you're looking at in front of you is the, oh goodness, where's my pointer? Just 1 second. I want, here we go. Here we go. This is the 15-inch Mertz and Merler telescope dome, and the archive that we're going to talk about very much is over here. Harvard has over 550,000 glass astronomical plates. It is by far the largest collection in the world. And they wanted to digitize most of the plates. And the whole idea is to allow for, no, what is this popping up over here for? Okay, to allow for the study of these, and especially to know two things: astrometrics and magnitude. Astrometrics is positional data, and magnitude they wanted to within 1/10 of a magnitude of over a 100-year time frame. That is what we are looking at here, and the talk is going to start with talking about what the Harvard plates, how they came about, what this project was about, the issues of making a custom-made scanner, and finally what the results were. So there's 3 issues here. The plates, the whole thing was started by Professor Pickering. There were some pictures photographed beforehand, but what you're talking about is, again, photometry and astrometry. You know, in astrometrics, I first discovered on the Star Trek Voyager series at an astrometric lab, right? It was only with this I really got to know what it was all about. Harvard sent telescopes around the world to photograph the northern and southern hemispheres. Now, it says about 100 years continuous. Glass plates at one time were the way to make large photographs. They were larger, they were stiff, and they were made commonly through the 1960s. Kodak continued to make these plates specifically for Harvard, their #1 customer, even after they would have dropped it. Eventually, around like 1980 or so, they went to Harvard and said, we're not going to make any more. One last batch, you can buy what you want. They bought them all, and they sort of handed them out sparingly ever since. So in the last few years, very few were made. And in any case, one of the telescopes involved was this one here, which, by the way, took this picture that you see of Comet Halley. This photograph was taken in April 21st, 1910. It's a 30-minute exposure. This 8-inch telescope was set up in Peru, Arequipa, Peru. I'm probably mispronouncing that. Keep in mind, take a look carefully at the telescope. This is not what a refractor would normally look like for us, because this does not have an eyepiece at the end. It has a plate holder. That's why that stubby end to the whole thing. And okay, now this is the only fairly complete, there are gaps in it, but only fairly complete record of the sky for that 100-year period. So if you want a 100-year history of the astronomy, there's one thing, there are 2 choices: either digitize these or wait another 80 or 60 years, because they're making stuff right now. There's wonderful digital, the Sloan telescope and stuff like that. So the point is that now the other plate, as you can see, other plate archives lack the resources to complete this process. So now that this is largely complete, there is a possibility of digitizing some other plates from other observatories, but that's not an easy thing to do. Why would we do that? By the way, the background is M44, and that was taken with another, the 8-inch Ross Lundland telescope, by the way. When was that taken? this was taken February 15th, 1974. It's a much more recent telescope. One of the reasons for doing it is there are things that are very long variable. And this little baby has been coming up in conversation. T Coronae Borealis. It's a star that many people feel is going to get very bright. It's going to go nova this year. In fact, a lot of people were expecting it already. How would they know this? Because of studying the light curve from years ago. If you're talking about studying galaxies and quasars, the heart of the galaxies, many quasars are variable 10, 15-year intervals or more. So to really understand what's going on with these galaxies, with these quasars, you got to have a very long time frame. Now, and there is the telescope that took that picture, by the way. In the year 2000, the International Astronomical Union, they had their convention. They have a series of resolutions. The resolutions go A, B, C, A1, B, A2, A3, and B1. And this is resolution B3. Okay, that's where that number comes in. Safeguarding information on photographic observatories, and the actual document is on the right if you wanted to download it. But in any case, it was a recognition that they had already lost plates. Some were destroyed. And they needed to digitize and preserve these things. But it's not just preserving. It's preserving and digitizing in such a way that they can be used. Because just having images alone is not enough. So let's deal with this a little further. This happens to be the Large Magellanic Cloud. I'm going to repeat this picture quite a few times. This image was taken October 27th, 1949 in South Africa using the 24-inch Bruce doublet. Now, this was made by Alvin Clark. This is a 1-hour exposure. You will see this 24-inch refractor used elsewhere. It was moved around. Many of the there were 660,000 exposures taken. 550,000 survive today. So that's how many Harvard lost. And other observatories have lost others also. Some are broken, dropped, or what have you. Some people, scholars took them home and used them, and maybe they passed away and the family turned around. So I don't know what this thing is, throw it away. And we will deal with some instances why some larger sections were lost. But this is roughly how many survive today. Okay. In the 1950s, Director Donald Menzel stopped the survey. Now, he was assistant director starting 1952, and then in 1954, he became the director. He continued on to 1966. I don't know the reason why he stopped it. There may have been very serious reasons why Harvard was not going to finance this anymore. I don't know. But a lot of people would practically spit on the ground at the very mention of this man's name. He created such hostility. He also, and they call that the Menzel gap. He also destroyed an unknown number of plates. Now, this caused all kinds of upsetment. They thought hundreds or possibly thousands were destroyed. During the course of this project, they found many of them. And in looking at the quality, or really the lack of quality of the surviving plates, they realized the ones he threw out really were unusable. So some of the horror that they thought that Menzel had been doing is gone. But there's still the issue of the gap. Okay. Now, the status. Scanning was completed on March 28th of last year. 470,000 plates were scanned. Remember, there's 550,000 total, but some of these, the other 80,000, if my math is right, uh, are of other types. Some of them are small and they're photographs of other things. They're not sky survey. Some of them are these wonderful pictures that we use to break up the stars into their spectrum, and they require a different kind of a scanner. Some of them are film. But nevertheless, the project itself ended with 470,000 plates. Now, I am going to digress for a bit and talk about this wonderful telescope, the Mertz and Muller 15-inch, without touching the brightness and contrast. The picture I got on the right, because I took these pictures, was dark. I touched it up to, you can see that beautiful mahogany tube and brass, although touching it made it look a little more beat up than it really is, but that's okay. I had to show the mahogany. The telescope is absolutely wonderful. It is used for some public observing. What you see here, the wonderful clockwork, and you see that curved handle on the left. That's going to be next to me here. Yes, that's me with darker hair because I did this 20 years ago, but nevertheless. And I was sitting there to prove a point, by the way, not just to be in my own slide. That seat is how you observe with that telescope. The seat is on a curved platform, and as you turn the wheel, you can go up and down. While the whole platform, there's two ladders because that bench could hold two people, and then the platform can move right and left, and that way you can follow what the telescope is. So the telescope is moving and you're moving at the same time. And I can tell from personal experience, it's not difficult to use that. I thought it was going to require a weightlifter's arms to use it. No, it's actually very good.
What are you actually looking at?
Nothing. I'm trying to act intelligent. The question was, what was I looking at? Okay.
No, I mean, when you're actually using stuff.
What are you looking through? You're going to look at this. This is the eyepiece. Oh, I thought you meant what was I looking at? I was just posing. Yeah, down here. Okay, the eyepiece. I just photographed the eyepiece holder just so you can looking at this. There were over 20 different telescopes used for this project. The smallest was a 1-inch refractor, and the largest was a 61-inch reflector. This was a massive project, and it was sent all over the world. They did have problems with the plates, and one of the problems that now this is by the way, this is this particular 10-inch triplet is mounted in South Africa. It was made by the Reverend Joel H. Metcalf. There's a historical photograph on top. It has been restored and repainted. It's now used for public observing. But in any case, you can imagine going all over the world, into the Andes, into South Africa and other places. They also did Mount Wilson. The conditions were very rough. They had bad weather. In case of the telescope in Peru, they even had gotten to the middle of a revolution. They also had problems with weather. And I read some of the notebooks, and I tell you something. One was that it was clear all day, and the minute the sun went down, it got cloudy. It was cloudy all night. Can anybody relate to that? I think we all can at one point or another. But there was another one where I read the notes, and apparently it went below freezing just as the evening came about. And so the dew that formed on the shutter froze the shutter solid. Now, we don't think of that with electronic telescopes anymore, but it's understandable, right? But you probably never experience an insect dropping dead on your plate. Okay, there's also one of a spider. they believed that they could identify the species of praying mantis that was. This is the kind of stuff they had to deal with, but they also had tragedy that was not funny. For during the Second World War, the plates in South Africa piled up because they didn't want to risk it being sunk. It'd be destroyed on the way up. Finally, by July of 44, the German subs were really tied up just trying to take care of the convoys going across the Atlantic. They were losing the war. So, well, this is time to bring a shipment of plates up. And on July the 25th, off the coast of Africa, this ship was sunk. And Robin Goodfellow is an it, not a person, by the way. See me afterwards about that. By that. Okay, that is a specific type of submarine, a type 9D2. It was a extra long distance sub. It was also a cargo sub. It was going to Japan. Actually, it went to Indochina, what's now Vietnam. Okay, they called it then Indochina. And it was carrying a load of, now this is where my research came in. Was carrying plans for weapons because the Japanese needed that. It was carrying some aluminum that Japan was having trouble producing, and it was carrying optical glass. And this sub carrying optical glass destroyed a ship that was carrying these glass plates. If that's not awful, I'll tell you something. Another sub that was on the same mission sunk another cargo ship. The sub captain was Norwegian. His father was on the crew. The father was with the Allies and the son was with the Germans. This is worse than the story in my own family, tell you the truth, because my father was German and was in the American Army. But that story you'll have to ask me about later. Nevertheless, this was something, they knew it was sunk. They didn't know the other story. And I researched the rest of this. This is the archive. The important thing, most of the archives are here, and some of it up here. The office is up here. This section of the archive building is now a meeting room. And who meets there but the ATMs of Boston, the Amateur Telescope Makers of Boston, right across the hallway from the office. By the way, here's the big dome that I was in beforehand. I don't remember what telescope is in this dome. This is no longer in existence. Okay, this has been torn down. So far, so good. This is the whole thing from a more recent picture from Google, and this is where that small observatory was. This is the big one, and here's the archives. January 2016, there was a flood. A water main that was in front of the building flooded. So I said, okay, these terrible things happen, but it was something weird. It wasn't the water main going to the building. The municipal water main crossed the property and went, and it was the municipal water main. I have never heard of a municipal water main crossing private property. In the course of my work, I've seen cases where a water main will be, or other utilities will exist because a street was demapped and the property owner has to deal with these legacy things, but this was actually put there. I have no idea why. Nevertheless, this is the archives, the downstairs, and what you're looking at on the left is what most of it looks like. You have cabinets that holds the plates. On this image here, you see card catalogs. This is a light box. This is designed for observing the plates. It's one of several. And what you have, tell me what happened. Oh, okay, wrong button. This is an example of other plates. Now, most of the plates are 10 by 8. That's what we're looking at here. That's what we're looking at here. These are smaller ones. They're not, the scanner is not going to work on these. There are larger ones that are, was it 11 by 14? the 10 by 8s usually cover 30 degrees of sky. You would, and then you notice that on the previous pictures that I saw. Now, that's an example of card catalogs. Remember those things? I mean, if you have 550,000 plates, that's going to be a lot of cards. But that's information was put into notebooks. Those notebooks, there's 2 rows of these, one in front of the other. The older ones are here. And then they got standardized. I'll deal with that in a second, why they were standardized. Here are 2, these are filtered cleaning stations. Now, they're similar to what Tony Pereira has in his factory, where you have to have filtered air and where people clean optics. These don't require the high level of care that Tony would have for coating, but nevertheless, you get the idea. It serves the same purpose. But in the background is the access to the basement. And let me tell you something, that is narrower and steeper than it appears to be. This is very difficult to get down or up. So during the course of this project, where they realized that people are actually going to be working here for a period of time, there were 2 of these spiral stairs, but they're no good. So they decided to put in an emergency exit. There is a problem. The ceiling is only a few inches taller than I am. This is their emergency exit. You crawl up, open the handles of the window, and literally crawl out on your hands and knees. That's how you get out in an emergency. See, the building is protected. It's a historical building. So, and this is a very wealthy area, and they have these things, and so it's landmarked. So they cannot work on the outside of the building. It couldn't change anything, even putting in a door there. And you could have cut out part of the ceiling, put in a, but that wasn't work. So this is what they did. Now, the scanner would go in behind this wall on the right. They put in AC, and there's a filter. So we'll deal with that in a little bit also. I have no idea what the DVD is all about, by the way. I would not want to be here in an emergency. That's also why the water only went up a few feet, because it got to ground level. Okay. So great, you have scanners. So first thing they did was buy a $50,000 Creo Cytex EverSmart scanner. 4,800 DPI, wonderful. 20 minutes a scan when it wasn't breaking down, which it did often. At 20 minutes a scan, it would have taken 60, maybe 80 years to scan all the images. Not a good idea. Okay. By the way, I stuck here also something else. Remember Clyde Tombaugh had taken 2 images of Pluto, and he knew he had something? They went to Harvard. They went to the Harvard plates and found planet X. Thus, they had image number 3 and could then calculate its orbit. That was one of the reasons for it. This is also used today when they find very slow-moving things, asteroids, particularly the ones further out, which are slow-moving. So this stuff is still needed. So, okay, that scanner didn't work. They would get another one, and this is the UMax PowerLook 3000. It's a $5,000 scanner, 1,200 DPI. Here's the same plate. You see the problem? They lost a lot of image. Never mind, it's 10 minutes a scan. It would still take decades to use. These commercial scanners would not work. Another issue, okay, what they found out, they need about 2,400 DPI something between these two. They need 1.2 micron positional accuracy for the astrometrics. This is not easy because your scanner has moving parts. To be accurate within 1.2 micron, this is cute. And it has to be high speed of the 300 plates a day. The reason for 1.2 2400 DPI is when you have too much DPI, or the expression too much information. What happens when you magnify film too much? You're magnifying the silver halide crystals. That's too much information. No such scanner existed. They were looking at this. They needed to do something. And so what do? Alison Dunn was the curator. We're up to 2002 now. But she decided to walk, she's in her office there. She's showing how to handle plates, by the way, by touching them only on the edge. She decided to walk across the hallway to a meeting of the ATMs of Boston, the Amateur Telescope Makers of Boston, because there was a lot of talented people there, and she was hoping that somebody could help her. It just so happened Robert Simcoe, who's an electrical engineer who specializes in computers. Back in the day, a lot of the stuff that we look at that comes automatically on a computer, people like him developed. And he said, you have only one solution. You have to build a custom-made scanner. And that's the next step of this project. They started with a camera. This particular camera, the sensor is 45 millimeter by 45 millimeter. It's a $10,000 camera. Very wide dynamic range. A lot of people don't appreciate what a dynamic range is, but I had a beautiful HP printer, and somebody said, oh, you could save a lot of money, get an aftermarket toner. And when you were printing black, like these letters up here, worked perfect. The paper was white, the black was, but then when you go for grayscale images, it didn't work. It didn't have the dynamic range. You could just see it didn't work right. This has a very wide dynamic range, could read out 12-bit digitized image at 140 megabyte per second, which, take my word for it, that's fast in 2002. USB 3 could handle it. Now for a light source. Okay, they got this. I don't know if I mentioned that camera was about $10,000. Okay, this here was this particular light array from Laminar Ceramics, red. Remember, if you use one color, you get sharper images. Okay, you're not dealing with chromatic aberration. That's one of the reasons why people have those funny glasses to read when they're driving in twilight, so that you can blue blockers, something like that. 4 of these, they were unusually bright for that time. They advertised these sort of 10 times brighter than the competition. This is unusual. It was 117 LEDs that you're looking at there, times 4, and this would be their even light source. Now, what about the lens? This monster is a foot long. This is a over $5,000 lens, and all it does is does not magnify. It just transmits onto the sensor exactly what was done with a very, very flat field. So flat that each photon being picked up would land exactly on the proper pixel on the sensor. One of the fellows, Ed Loss, later told me that this is actually overkill. This lens was overkill. They actually, by the way, this was actually donated. But in any case, there would be no loss of data. Very important for them to have no loss of data. They built a scanner. Aerotech is a granite, super polished. This is almost photographically polished. Okay, 2,400-pound scanner. It was put in the basement because the basement is on poured concrete. Back in the 19th century, what they would do is expose the bedrock and level it with concrete, even if it was 7 feet thick. They at Harvard was saying that this was built to be resistant to earthquakes, they were wrong. I spoke to an engineer. Okay, that no, that's how they did things. An engineer who specializes in renovation, by the way, because he had to know all the old codes. Look carefully. On the left, there are 6 DB25 cables. USB at that time was in its infancy. DB25 was faster at that time, and the hardware was highly available. Okay, the blue hoses are for air glides. It's compressed air. On the back, we'll get into this a little bit. That was a zero-door glide slide. They're for positional accuracy. There's scales, zero-door scales. Okay, we'll deal with that in a little bit. And you can actually see a reflection of these cables in the scale. Zero door is a type of clear ceramic that does not have a coefficient of expansion. It doesn't expand or contract with changes in temperature. I mean, it does to a tiny microscopic level. But the point is, it's essentially zero. Bringing it in, this is what will later become the emergency exit. The distance between these columns is 55 inches. This scanner had to pass between these columns. So this is why they only had a 2,400-pound scanner. They wanted something larger. They wanted overkill on everything. Notice neither of these guys is very tall. Believe me, I know what being tall in a small room is all about. That ceiling is a lot closer than you think. Okay. And so they had to use it on the floor because that way, by the way, that's an asphalt floor, by the way, asphalt tiles. But that way there would be reduced vibration, and also so they don't have to bring the tiles up and down those spiral stairs. Here's the assembled. You have the lens, the camera. We'll talk about the glass plates in a minute, but this is holding 2 8x10s. The larger plates are 14 by 17. We'll deal with that in a second. You have it all assembled. Now, the air glides. The Robert Simcoe knew that there was a problem with trying to scan. You can get interference. And there's a special type of glass that will not have these interference patterns. They're called anti-Newton ring glass. So he called Gray Glass Corporation in Queens Village, asking it to order this. And it just so happened that the person who answered the phone could convince him that that was not the right, that he needed to design it better. Because the person who answered the phone was Bart Freed. And Bart, as he's talking to Robert, Robert was very surprised to find out that Bart knew about astronomy as well as being an expert with glass. And let's just see. Bart, and this is a quote from his comment, "A bell rang in my head, and I asked him if these were astronomical plates, and he was surprised and asked how I knew that." Because he described that it was from Harvard. That's what. And then I described my deep interest in the subject, and together we discussed what he needed to accomplish, which was much more than simply avoiding Newton's rings. The light source illuminating the plate had to be to transmit uniformly to the detectors. I designed a diffuser made from a 3-layer glass sandwich, creating the top layer out of shot opalica glass. By the way, zero door is also made by shot. A white flashed opal glass, and on it is, and finally so this 3-layer glass was what they developed. By the way, here's another view of the calipers. You don't see it, maybe a little bit over here, but there's a series of lines for 0.2 micron positional accuracy. Can you imagine something being able to move around and be to 0.2 microns in accuracy? Of course, being that these are astronomers, we always have to have something silly going on. Okay. Nevertheless, now this is Allison Dunn, and what she's doing here is examining glass and cleaning glass. On the pictures on the right, keep in mind that photographic plates have emulsion on one side and they're clear on the other. I mean, there's nothing on the other side. So the back side, she's cleaning on the right of these two slides, and she's using regular window cleaner because that's clean glass. On the emulsion side, she has to do this very carefully, spot every bit of dirt and carefully wipe it off. In order to make sure there's no dust around the scanner, it's an isolated room. They've had to put filters on the old steam radiators. And then on the right, they installed finally in June 2010, they installed a AC unit to keep the temperature stable and comfortable. Now this happens to be the hands of Ed Loss. Ed Loss, and I misspelled his name in the emails I sent out. It's L-O-S, not L-O-S-S. He is putting down 2 plates for scanning. Now remember, it had been, how do I get this to work? Now, darlings, how do I get this to work? Okay. I had a video. I just want to see if I can get the damn thing to work now. Okay, I'm unable to show this, but it takes 30 seconds to scan the 2 plates rather than 20 minutes on the cheaper of the scanners. You get the point, though. I didn't get this to work on this computer, too bad. Why is this now? Now I'm not getting anything to work. Okay. The first scan they made on November 21st, 2005. The reason for scanning Rho Ophiuchus was because this has dim stars, it has bright stars, and it has nebulosity, all the nonsense that's going to occur. So they could then test this and see, was everything right positionally? Was it showing what it's supposed to show? They studied this after scanning it. Now here, Allison Dunn is doing more care, is showing how to put a glass plate onto, put an envelope onto it. Nothing must touch the emulsion side of the plate. They did allow me the freedom to walk around and to photograph what I wanted. And so here's a damaged plate, and here's another one. These are the 14 by 17s for scale. Here's, they left I don't know why that staple is on there, but I didn't touch it. Ed Loss was able to write software that would eliminate those lines where the cracks were. So the information left on the plate was still there. Now, how you don't deal with the positional changes that occur when glass changes, I don't know. Okay, all this is fine, but you need information from the notebooks. And here is Holly Klug. Here we are in an office on the main floor of the American Museum of Natural History. Yes, I spoke to everybody they spoke to. Holly had helped organize a group of volunteers who what Harvard did was photograph the books, send her the images, she would send them to volunteers who would carefully transcribe information, and they had checks and balances to make sure everything went right. And there were 1,200 logbooks. There are a lot of stuff. This project, and all that information was put onto Excel spreadsheets. Holly Klug said something that really stuck out to me. You could see in those books how dedicated these guys were, the astronomers. They were out there Christmas Eve, Christmas Day, taking pictures for a project that they themselves would never see the results of for future work. That we don't always appreciate that there's these people are how dedicated, and we get the results of this, the benefit of this. Here's an example. Now, the early log books, they were just plain line books. And they were difficult to read. People were told to put down this information, but people didn't quite know what. So, for example, they were putting down what they thought was important, but like they had to put down the time. And some of them were using universal time, some were using local time or local sidereal time. Ed Loss said to me, with some of the plates, if we understand the time correctly, then the image must have been taken during the middle of the day. If we understand the positional data correctly, they must have had the telescope pointed at the ground. In other words, there were problems here. So they standardized the plates with these more involved log books here, where they trained the people how to use them. By the way, one of Bart's friends, Al Lamperti, did I say that right?
Yeah.
Okay, was one of the volunteers. By the way, she wasn't Holly Klug when I met her, that she was engaged at the time, but her name is now Holly Klug. Okay, but you see how things are standardized, and on the right is where the notes would be. And like I said, I read this particular one does talk about some sort of difficulties that they had, which is now, years ago in 1922, this was a great way to measure brightness of stars. A standardized light source going in here, he would compare the star to the standardized light source to tell the brightness of the star. You need to be able to get that information automatically. So just having images is nice. But they realized they needed one other thing, and that was to get the positional and brightness info off the plates. So just digitizing them is not enough. This brings us to a program called Sextractor. Now, Sextractor sounds like something you're not allowed to teach in public schools in Florida. But the fact of the matter is, it's source extractor. Again, somebody's being a clown, but it's and it draws from the plates this information that's desired. Now, and you can get this, by the way. It's possible if you wanted to do this for your own images. Another problem, these are the sleeves. There's wonderful information on it. It has a number, talks of what was positional data, date, exposure in time, wonderful. Except over the years, people put them in the wrong envelopes. Somebody may have had a couple of different, and they put it back in the wrong envelopes. What to do? Because these things are worthless if you don't know what they are. Let's talk about another telescope for a moment. The Sloan Digital Sky Survey. This is every clear night, this telescope takes images. But the way it does it is the telescope remains stationary and the sky moves across. And then each night that you point it in a different direction and the sky moves across. Tremendous amount of data. And you see these images that are coming out of it. They're not the greatest pictures of these particular objects, but they're wonderful. However, there are three pieces of information they need. They need to know where the telescope was pointed. They need to know, you need the output from the camera. You need to know at what elevation, what direction the telescope was pointed, and you need to know the time. It needs to be, when they were running this thing for a while, it turns out that the time data was lost. So they had these wonderful images that had no idea what they were for. Same problem that Harvard was having. Some people decided, these people in particular decided to make a project out of writing software for this. And I got in contact with David Hogg. Now, here's how they analyzed. This is how they approached it. I want you to imagine that you have a picture of the sky that's in that green box. Where in the sky could this possibly be? Well, download onto the computer 2 catalogs. The US Naval Observatory B, which contains 10 to the 9th power objects. 10 to the 9th power means a lot. Okay, or the Tycho, and they also have the Tycho 2, which is a supposedly tiny subset of 2.5 million brightest stars. I will tell you right now, 2.5 million includes a lot of stars that aren't terribly bright, in my opinion. Nevertheless, here's how it works. You have these maps on the computer. Let the computer automatically scan, look at your digital scan now. And it will go, it will find a group of 4 stars. Doesn't matter which 4. It will automatically do an x-axis and a y-axis compared to where A and B are. A is 0, 0. X equals 0, y equals 0. B is x equals 1, y equals 1. C and D are some sort of fraction of that. Now that 4-star pattern is a number sequence. Go ahead and find the same number sequence on so you have this, the picture you took and the sky survey. Find a number sequence and compare that to the known objects. It will automatically take into account orientation and size. This is so good. It is designed deliberately to have both positive and negative. So it doesn't matter if we're talking about a refractor or a reflector. Doesn't matter what the orientation is, doesn't matter what the size is, doesn't matter at what angle. It will automatically fit it in. And there you have it. David Hogg said to me that he basically has 100% accuracy on this because it does other checks also. It's turning a massive problem with a lot of data into just a number problem, and computers are really good at that. And by the way, this is just part of a PowerPoint that they have. I just used some of the pictures. But then later on, I corresponded with Mr. Hogg. You can see his email in the middle. And later on, I met him when he was giving a presentation on this software at the American Museum of Natural History. Yes, I went back there. Okay. Interesting thing. This is so accurate positionally that not only will it tell you what the object is, but it'll correct for the astrometric changes. It will be able to tell you when it was taken within plus or minus 2 years. That is what I call amazing. And very good for people who don't know where their glass plates were. So that took care of that problem. The first place scanned, like I said, the Rho-Ophiuchus complex. This particular image was taken July 8th, 1899, and was scanned November 21st, 2005. But after that, they went on to M44. The reason for studying M44, to take a series of tests, was because this star cluster has been very heavily studied. A whole lot was known about it. So they would take a few images and make sure that the scanner was working right and doing what it was supposed to do. So that this particular image of M44 was taken February 15th, 1974, using the 8-inch Ross London refractor, 15-minute exposure. What they did was then to study some stars on it. And one of the things they first found out was that one of the stars was, and in fact more than one, were variable, and they didn't know that. because the level of variability was never caught previously. So they already were getting information that was not known. I wound up writing an article about this. What had happened initially was I met Ed Loss. Well, he was the fellow at the scanner on the video that I could not see, that I couldn't show. Ed, I met him going to the Stellarphane convention in Vermont, the Amateur Telescope Makers Convention. We're at the same bed and breakfast. Ken goes there also. And what happened was he's one of those fellows, if you ask him a question, he's going to talk for 5 or 10 minutes and put an encyclopedia worth of knowledge into that. I'm talking to him, I realized, this would make for a good talk. So I started, can I take notes? And finally I realized, something, this would be a good idea to go up to Harvard and photograph the whole thing. Then I'm thinking, well, going up to Harvard to take a, might as well submit it to Sky and Telescope. They ran it. It's listed over here. Here's the article, part of the article. It was published in March of 2010. The senior editor of Sky and Telescope, Robert Nye, because you have to understand, he's on first name basis with the people there at Harvard and with the ATMs of Boston. He's a member, was a member. He took the manuscript and went there, or the digital manuscript, and he said, what's the story here? And they were telling him, we learned stuff. We didn't know this stuff. This guy did his homework. He later said to me over dinner that this was one of the best research articles he ever had the honor of publishing. Okay. When a person, a professional, says to an amateur, I learned from you, that means something. Sam Storch said that to me a few months ago, and I will remember those words to my dying day. It really meant a lot to me. But Suman Tang, a doctoral student at Harvard, published her doctoral thesis, and she cited this work that was in Sky and Telescope, because she was working on this project. Okay. It was not wouldn't get too much attention right then, but Harvard now has potential difficulties getting foreign students, particularly people from China. She's working in California now, by the way. And for that reason, I'm going to tell you something that's not nice. The Harvard Plate Stacks is intending to have a century conference, the Cecilia Celestial Centennial Conference in October. And I got an email today that it is being postponed to the springtime. They didn't even update the website yet, due to current circumstances. Read between the lines. Okay. The only other difficulty that I did hear about this whole project was when it was published in Sky and Telescope, the people at Harvard had never told their bosses. And the people, the administration of Harvard said, we want to control the release of information, because they were intending to keep this, once in a while have an article in Sky and Telescope or wherever. But hey, too bad. That I don't care about. Okay, this is from the DASCH website, and be aware that this is data release 7, I believe, was the last one. You can go to the data, download this data also. And by the way, the other things I talked about, Sextractor and that other software, you can use it. You got to ask for permission, but a serious astronomer amateur astronomer is capable of using these if you have need for them. And that is really, let me just see something. Oh yeah, one little thing. The 24-inch Bruce doublet was also used in Peru. I do not know why this particular observatory, which used to have a roll-off roof, had this fancy front. But in any case, it has, instead of studying the heavens, it's used to study heaven. It's now a chapel with a new roof. Okay. By the way, this is the Harvard this is the big telescope. This is, I believe, is the one that was torn down more recently, and the others, this is the yard which had the famous water main under it. End of story.